Assalamualaikum. In this video lesson, we again illustrate an application of Newton's three laws of motion on a two-body system, which is either in a state of dynamic equilibrium or accelerating uniformly. So just stick around till the end of this video. Watch and learn. Before we go to our main lesson, let's first have a practice question. Two boxes of masses m and 3m are stacked. See figure below. The surface between the more massive box and the horizontal surface is smooth, and the surface between the two boxes is rough. If the less massive box does not slide on the more massive box, letter A, what is the static friction or static friction force on the less massive box? Choices are letter A, F, letter B, F over 2, letter C, F over 3, and D, F over 4. And question letter B, what is the coefficient of static friction between the two boxes? Choices are letter A, F over 4 mg. Letter B, F over 3 mg. Letter C, F over 2 mg. And option D, F over mg. So in the first case, the correct answer is option letter C, F over 3. And in letter B, the correct answer is option letter B, F over 3 mg. We emphasize that the smaller mass or smaller box is at rest with respect to the larger box, right? So, because the surface between the larger box and the horizontal surface, okay, is smooth, so there is no friction, right? But between the smaller mass and the larger mass, which is considered rough, there must be uh, a what we call static friction that prevents it, right, from starting to move relative to the larger mass. Okay, and we denote that limiting friction as F sub S, right? F, F sub S is the static friction uh, that the smaller box experiences as a result of the motion, okay, resulting from the applied force F, since it's mentioned in the problem that the smaller box moves together with the larger box, right? So this static friction can be expressed as the product of the coefficient of static friction between the surfaces of the two boxes. All right, that is mu sub S right? And that will be multiplied by the normal reaction force n sub 1, where this normal reaction force n1 is just equal to the weight of the smaller box, equal to mg, right? So we emphasize that this static friction is the friction that is experienced by the smaller box, right? And uh, since the two boxes are in physical contact, okay, the same coefficient of static friction is also or also exists, okay, as far as the larger box is concerned. In other words, we can also express this coefficient of static friction in terms of the force F that is applied on the larger mass. That is, mu sub S is also equal to the force F, all right, that is applied to the bigger or larger mass, divided by the normal reaction force N sub 2, right? Where the normal reaction force N sub 2 is equal to the weight of the larger box, which is 3mg, right? Take note that uh, the question in letter A is uh, what the static friction is, okay, on the smaller box, right? While we have the standard definition of that static friction equal to mu sub S times mg, but uh, notice in the options given for question letter A, we want an answer that is expressed in terms of the applied force, capital F. All right? So the static friction that we want exerted on box M, or the smaller box, should be in terms of the force F. All right? And that is, right, using the formula for the static friction exerted on box M, which is mu sub S times mg, right? We can use the equivalent definition of mu sub S equal to F divided by 3mg. We just substitute this here, all right, in the first equation. So instead of mu sub S, we express that in terms of F divided by 3mg, right? But there is still mg to be multiplied to mu sub S. That's why we came up with this equation for the static friction exerted on uh, the smaller box, right? In short, this static friction experienced by the smaller box is due to um, the upward reaction force of the larger mass as a result of uh, the force or the weight of uh, box M, okay, on the larger mass. So the reaction to that, right? The reaction of that force exerted by the smaller box on the larger mass, okay, is the one responsible for the static friction, all right, that is experienced by the smaller box, right? And here, uh, we can cancel out mg so that we come up with our final answer for letter A, which is equal to F divided by 3. right? So this is the static friction that is experienced by box M. And in our diagram, you will notice that that force F over 3, okay, balances, meaning it is equal but opposite to the static friction. And that explains why the smaller box, okay, remains at rest relative to the larger box. It does not slide over the larger mass. And moving on to question letter B, which is asking for the coefficient of static friction between the two boxes. All right. And since the same coefficient of static friction exists on box M as well as on box 3M, therefore our answer to question letter B is just mu S equals force capital F divided by 3mg. So moving on to our main problem. Okay, we have here the question. Block A in figure A weighs 1.20 newtons and block B weighs 3.60 newton. The coefficient of kinetic friction between all surfaces is 0.300. Find the magnitude of the horizontal force F necessary to drag block B to the left at constant speed. If, letter A, if block A rests on block B and moves with it, that is shown in figure 1-A. And question letter B, if block A is held at rest, and that is shown in figure B. So the diagrams for the main problem is given here. This is for question letter A and for question letter B. Take note that in situation letter B, block A is held by this rope attached to the wall. Identifying the given data, we have the width of block A denoted by W's of A equal to 1.20 newtons, right? So this applies to both situations A and B. Also, the weight of block B, denoted by W sub B, equal to 3.60 Newton. And the coefficient of kinetic friction between all surfaces, denoted by mu sub K, equals 0.300. So our first target variable is the magnitude of the horizontal force F, okay, that is necessary to drag block B to the left at constant speed, all right? If in situation A, block A rests on block B and moves with it. And in situation B, if block A is held at rest. So moving on to our computation, all right. Um, in the figure A, blocks A and B, okay, are treated as a system. And since it's mentioned in the question that both boxes or blocks A and B will be moving at constant speed. That means the summation of forces along the horizontal must be equal to 0. Right? So, at dynamic equilibrium, while the system blocks A and B are moving to the left, right? Because of the application of the force F, we say that there is an opposite but equal opposing force, and that is the force of kinetic friction exerted on uh, block B, and that is represented here by the red arrow directed to the right, opposite to the applied force F. And this applied force F, which is our target variable, can be expressed as being equal to Fk sub 1, and that is also equal to the coefficient of kinetic friction multiplied by the reaction normal forces, right? Which happens to be equal in magnitude to the weights, right, of the two boxes or blocks, all right? N sub A refers to the normal reaction force, okay, exerted by block B on block A, while N sub B here is that of block B, all right? And we can substitute, all right, since the coefficient of kinetic friction, all right, in all surfaces, okay, the surface between the between block B and the horizontal surface is just the same as the coefficient of kinetic friction between the two blocks, right? So that is equal to 0.300. Multiplying this by the sum of the weights of the two blocks, right? So 1.20 newtons is uh, the weight of block A, all right? While 3.60 is the weight of block B. So when you do our math, we arrive at the value of the applied force F equal to 1.44 newtons. So if this amount of force F is applied on the system, all right, uh, with the two boxes moving together, okay, at constant speed, the force that is necessary is equal to 1.44 newtons. Moving on to question letter B. We're looking for the force necessary for block B to be moving at constant speed, right? Um, but this time, block A will stay at rest because it is being attached or held by the rope attached to the wall. So this time, we consider the forces on block B only, right? The fact that it is also moving at constant speed Therefore, the summation of fx equals 0 also applies. And as shown in figure B, right, there is an opposing kinetic friction on block B, okay, from the fact that it is in contact with the surface, right? So F sub K1 is the kinetic friction between between block D and the horizontal surface. So that the direction of that kinetic friction is of course opposite to the force capital F. That is directed to the right. But at the same time, right, there is another kinetic friction between the surface of, or the lower surface of block A and the upper surface of block B, right? And we denote this by F sub K2 and represented by the blue arrow directed to the right. So Fk2 is the kinetic friction from block A, since we're talking about forces on block B, right? That is how we define Fk2, right? Kinetic friction from block A exerted on block B. So it's equal to the product of the coefficient of kinetic friction and the normal force or normal reaction force, right, exerted by block A on block B. That is, Fk sub 2 is equal to the product of 0.300, that's the value of mu sub k, and the weight of block A equal to 1.20 newtons. So we get, right, the magnitude of the kinetic friction number 2, or F sub K2, equal to 0.360 Newton in 3 significant figures. So we can now execute our dynamic equilibrium equation, or the summation of Fx acting on block B, which is equal to 0, all right, with the force F already isolated, since it's our target variable, right? So capital F is just equal to the sum of F sub K1 plus F sub K2. That is, F equals 1.44 newtons plus 0.360 newtons. So we get the value of the force necessary, all right? F equals 1.80 newtons, also in 3 significant figures. And that ends our tutorial lesson for this topic. Till the next episode, mabuhay, mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.